Hello students, welcome to Time classes. Hope you are doing good. In this session, we'll discuss about light. In that, reflection of light. We have our eyes to see the beautiful world. Suppose you are in darkness. Can you see? Appears to be a silly question, right? We can't see. So what we require? A light. So light enables us to see the world. Okay. So there's a source of light. Suppose you are in a dark room. You lit a candle. The light from the candle is emanating in all possible directions. Okay. So this light from a source, when it is going in all possible directions, the path along which light travels, we call it as a ray of light. It is for our understanding that we imagine the light rays coming from the point source and traveling in all possible directions. May be difficult to visualize this. Sometimes we may be able to see some of the spectacular scenes like this. See how beautiful it is. The atmosphere is completely cloudy over there, but in between you have a narrow opening for the sunlight to enter into the Earth's atmosphere. The light rays are piercing through the small opening over there and reaching the Earth's surface. Now you will be able to see there is a narrow streak of, as if a streak of light coming from the sun and receiving on the earth and being received on the earth. Okay, so this is what we call it as a ray of light. Fine. How far is the sun from the earth? Sun is our ultimate source of energy. Okay, when you consider the distance between the sun and the earth is too far. Do you know something like light takes approximately 8 minutes to travel from sun to earth. In traveling this distance, it passes through vacuum. There is no medium between the sun and the earth. Okay. So even though it is traveling through vacuum, it does not mean that it cannot pass through a medium. Okay. It can pass through the medium also. It passes through the air, glass, oil, water, etc. Some medium will allow light to pass through partially and some does not. Okay. So it is based on these objects what we define two major phenomena related to light which help us see the world. That is reflection and refraction. Okay. So before going further, we'll discuss some of the properties what we have seen through this particular 2 minutes of time. Okay. So first of all, we define light as a form of energy which helps us see the world. Okay. So when you consider the properties, it travels in straight line. That is what we discussed already. We call it as rectilinear propagation. Okay. It travels in the form of electromagnetic waves. Okay. And with a speed equal to 3 into 10 power 8 meters per second, which is the speed of the electromagnetic waves. So as I told you, it does not require a medium. So these are some of the properties what we talk about. Okay, electromagnetic wave, yes, the waves which can pass through vacuum also. So they are also called as non-mechanical waves. Okay. Now, when we wanted to see the different phenomena related to light, out of which two major phenomena I told you, reflection and refraction, there are some objects which are associated with this phenomena. One is the mirrors and lenses. Mirrors are related to reflection and lenses are related to refraction. Not only this reflection and refraction, there are some other phenomena related to light. To understand that, but we need to know basically whatever we study under light, it is broadly called as optics. This optics is broadly divided into two categories. One is the ray optics or geometric optics, and another is the wave optics or physical optics. When we talk about the different phenomena which are coming under the ray optics, the major things is that reflection and refraction. As I told you, light will travel in the form of light rays. Okay. When I consider a single one, it is an imaginary line along which we assume the light is traveling through. The path along which light travels. Okay. That's what I call light ray. If I consider one more light ray like this, the red one, you can see these two are parallel. I'll call this number of rays as parallel beam of light. Okay. So when I say parallel beam of light, we also have a different kinds of beam. Suppose I'll take one more light ray like this. As you consider this violet or the purple one and the blue one, as they progress forward, the distance between them increases. They are coming from a single point and they are traveling in all possible directions. So such a beam which will distance in which the distance between them increases as they progress forward is called a divergent beam. On the other hand, if I consider this green arrow or the green arrow which is indicating on one more light ray, and if you compare this one with the red one, you can see as they advance forward, they will pass through a single point. So they are the convergent beam of light. Okay. So not only when we talk about the ray optics, we deal with the different rays. Okay. I'll tell you the purpose of this. The other branch is like wave optics or physical optics, right? So let us look at some of the phenomena which are related under wave or physical optics. We have the phenomena like interference, diffraction, polarization, okay, which you learn in the higher classes, which will be considered under the wave optics or physical optics. But as I told you, when you consider the light as wave, what type of wave is it? We already discussed it. Electromagnetic wave. Clear? So when you consider the electromagnetic waves, any wave in general, we do have some of the properties related to waves. What are the properties related to waves? One is the velocity or the speed, okay, frequency, wavelength. When you consider the speed of a wave, the frequency of the wave, and the wavelength of the wave, all the three are related with this expression V is equal to n lambda. V is the speed, n is the frequency, and lambda is the wavelength. Okay. Speed, what is the speed of the light wave? We discussed, right? It is 3 into 10 power 8 meters per second in vacuum. Please remember that point. From this expression, I can derive the expression for frequency. When V is equal to n lambda, I will get lambda is n is equal to V by lambda. Clear? What is it so significant about the frequency or the wavelength? But have seen sometimes the spectacular rainbow, which you detailedly call it as Vibgyor spectrum. So spectrum is nothing but arrangement of the frequencies or the wavelengths in a regular order. So here we talk about the frequency and the wavelength. Okay. So when I consider the wavelength of the Vibgyor spectrum, it ranges from 400 into 10 power minus 9 meter to 700 into 10 power minus 9 meter. The longer one will be having for the red color, the shorter one will be having for the violet color. So the wavelength of the Vibgyor colors will increase from violet to red. Okay. So any type of colored light, white light if you consider, which is a mixture of all these things, will undergo the reflection when it is incident on the objects. So we'll proceed ahead to know what is exactly reflection of light. When I consider reflection, how we define it? We define reflection as bouncing of the incident light from a surface. Okay, light is incident on a surface on an object. Okay, and that light is bounced. Okay, so when it is bounced, the surface can be a smooth polished or need not be also. When it is smooth polished and reflects most of the light incident on it, we'll call it as a mirror. Now see, for example, the light reflected from this vertical stack of mirrors. Okay, so we have a beam of light which is incident on each and every piece of the strip of the mirror over here, and this mirror is getting reflected. Okay, if I take very small pieces of the mirrors attached to a, suppose I stick small pieces of mirrors to a ball and suspend the ball and throw light from different directions on that particular ball which is hang the mirrors, stick to it all through the surface of the ball. It will be fun to see it. You might have observed such thing in an infotainment areas like this. Different color light is incident on it and they are getting reflected on different directions. Okay, so basically reflection is happening sometimes perfectly like this, sometimes may not be like this. Okay, so when you try to talk about the type of reflection, we do have basically two types of reflection. Let us discuss them one by one. The first category is regular reflection. Okay, what is regular reflection? Reflection from a smooth surface. Okay, wherever the surface is smooth like this, you have the incident parallel beam of light and it is reflected as a parallel beam of light. Such a reflection, you will call it as regular reflection of light. Where do you observe this one? Plane mirror, simple, right? We observe it in a plane mirror. If the surface of the mirror is not so smooth like this or it is not plane like this, then there is no question of observing a regular reflection. If not regular, then what type of reflection could it be? Guess. Yes, it is an irregular or diffuse reflection. So this can occur from any other surface which is not smooth and plane. Okay, so an example, if you consider this one, here the incident beam of light is parallel. But what about the reflected beam? The reflected beam is not parallel. Clear? So we can define both the regular reflection and irregular reflection in this way, where in the case of regular reflection, we can say that we can define the regular reflection like if a parallel incident beam of light is reflected as a parallel beam of light, then that reflection is known as regular reflection. And how do we define an irregular reflection or a diffuse reflection? Very much similar to the same sentence. If an incident parallel beam of light is not reflected as a parallel beam of light, this reflection is known as an irregular or diffuse reflection. Clear? Whatever may be the type of reflection, either regular or irregular, this reflection will follow some laws. Okay. So when you consider the laws of reflection, to understand this, we need to understand certain terms. And for our easy understanding, we'll take a plane mirror having a perfectly smooth surface. It is a plane mirror. So now I'll consider a light ray AO incident on the mirror. Okay. So O is the point of incidence. Now at this point of incidence, I'll draw an imaginary line perpendicular to the mirror surface, and that is what I call it as ON. This ON is nothing but the surface normal. Okay. So now these two lines are intersecting or meeting over here, right? So there is an angle formed. The angle between these two is called an angle of incidence. So this ON plays an important role in identifying what is the angle of incidence. So you define angle of incidence as the angle between the incident ray and the normal to the point of incidence on the surface. Clear? So now what is happening? The incident ray is fine, but what will happen? It is bounced. So will it bounce in the direction O to A again? No, it will bounce along the path O to B. So O to B is the reflected ray. Now this is also making some angle with ON. Okay. So this angle between the ON and OB, that is the normal to the surface at the point of incidence and the reflected ray, is called as an angle of reflection. Clear? Now, apart from this, we also need to know one more, which is called a plane of incidence. Okay, this particular plane, an imaginary plane on which this incident ray is AO, normal to the surface which is reflecting the light, okay, that is ON, the imaginary line, and the reflected ray OB. All these three are lying in this particular plane. We call it as a plane of incidence. So here PQRS is the plane of incidence. This is also an imaginary plane. Okay. So we are considering a path of light AO incident on the mirror at the point O. This O is called the point of incidence. Okay. Because it is striking the mirror at the point O, it is getting bounced off the mirror in the direction O to B. Okay. At this point O, we'll imagine a straight line perpendicular to the mirror. Okay. That is what you call the surface normal at the point of incidence. Then we have the angle between the incident ray and the normal, that is the angle of incidence. We also have the angle between the normal and the reflected ray, that is the angle of reflection. Okay. Apart from this, we also have some other angles, two other angles. Those two angles are nothing but, here you can see AOQ. Okay, let me show you clearly. Okay, this angle AOQ is called the glancing angle of incidence, GI. Let me write it as GI. So GI is called as the glancing angle of incidence. And this one here, this angle is known as the glancing angle of reflection, GR. Okay, clear? Now, with this information, we'll proceed to know what are the laws of reflection. The first one is that angle of incidence is equal to the angle of reflection. Okay, angle of incidence I is equal to angle of reflection R. That forms the first law of reflection. Second law of reflection states that the incident ray, that is AO, the reflected ray OB, the normal at the point of incidence ON, all the three lie in the same plane. That plane is nothing but the plane of incidence. That is the PQRS, the imaginary plane what we consider over here. We now proceed further to know the image formed by a plane mirror. So we'll take a plane mirror over here. The blue portion strip on the right side of this particular object over here is indicating the silver coated side of the plane mirror. The black portion is the reflecting surface. Clear? Now I'll take a point object. To know the position of the image of the point object, what we'll do is we will consider two light rays as shown. From the same position, these two light rays are incident on the plane mirror. They are reflected back. Okay. So once they are reflected back, if at all I wanted to see the image of the point object O, I should look at the for the image. I should look at for the image in this particular direction. Okay. So now the two blue lines which are indicating the reflected rays of these two incident rays are diverging. As you see, as they are moving further in the direction, as they are progressing further in the forward direction, the distance between them will increase. Okay, such light rays are called divergent light rays. Okay, so with such divergent light rays, it is not possible for us to form the image on a screen. So what we'll do is we will reproduce them back so that we will be able to know from which position they appear to diverge. So when you reproduce them back over here, the two reproduced light rays will meet at this particular point. That is the point where I will be able to get the image of the point object, say O dash. So if at all I wanted to know the position of the image of the point object O, this is the procedure what should I follow. This is with respect to a point object. With this particular knowledge, we'll try to know the characteristics of image formed by plane mirrors. Here I'm showing the image of a person looking into a mirror, and in the mirror he is observing his image. What is happening here? From the foot of the person, one light ray is coming over here and getting reflected on the mirror to reach his eyes. Same way, from the top portion, that is the head of the person, one light ray is incident on the mirror and then getting reflected over here and reaching the eyes of the person. Okay. So if you retrace these two back, and then likewise what we have done in the previous case for a point object, if we consider different points on the person, each and every point as a point object, and try to trace the image of those point objects, we will be able to get the point images of all those point objects, and finally we will be able to reconstruct the image, the total image of the person as viewed in this particular plane mirror. Now if you look at the characteristics of the images formed by this by this particular person in the plane mirror, the first and foremost thing what we get is the size of the image is equal to size of the object. Clear? So here you need to note an important point, that we will compare the size of the image with the size of the object. So size of the object is taken as the reference. It is not the size of the image which should be taken as a reference point. Clear? Reference object. So when I consider the size of the image, I will compare it with the size of the object, and then say in this particular case where the image is formed on the plane mirror, the size of the image is equal to the size of the object. Right? Same way, the image distance is equal to the object distance. When I say image distance and object distance, what is the reference point I am considering? I am considering the reference point as the mirror itself. When I say image distance, distance of the image from the mirror is equal to distance of the object from the mirror. So distance of the object from the mirror is known as the object distance, and distance of the image from the mirror is known as the image distance. So these two distances are equal. Okay, so these are all the characteristics. Let us see the next one, virtual. I just spoke about what is a virtual image. Virtual image is the image which cannot be caught on screen. So if you are looking into a plane mirror, you will be able to see your image, but that image cannot be caught on a screen. Okay, so you are able to get only the virtual image over there. And you can see the erect image. When I say erect image, the image is erect with respect to the object. Clear? So these are all the properties. And one more important property of the images formed in the plane mirrors is that it is laterally inverted. When I say laterally inverted, what does it mean? It means that the left side of the person is appearing to be the right side of the person. We'll see a small portion over here. See, you can see a small boy looking himself in the mirror over here. Small boy, the left side image is the person. He is looking into the mirror, and you can see the right hand he is putting forward. In the image, it is appearing as if the left hand of the image is putting forward. This is what I mean by laterally inverted. So we are not considering the point objects over here. So we are considering the total object and the image of the total object we are getting. So such an object where the size is bigger and not very small, we'll call it as an extended object. Okay. So hope the images formed by plane mirror is clear to you. Now we shall see some uses of the plane mirrors. Okay. So whatever the uses of the plane mirrors, first one, if you see, looking glasses. These are very much familiar for us. Next one is false dimensions. These are also one of the uses of the plane mirrors. When I say false dimension, suppose if I consider a room like this, okay, out of the 4 walls in this particular room, the 2 walls are fixed up completely with plane mirrors. You can see very clearly over here. See, there is a blue structure over here, and that blue structure is getting reflected in the mirror over here. So what is happening? Actually, the room is up to this particular dimension only. But because I have a mirror fixed to the wall over here, the rest of the room is getting reflected in that particular mirror, and it is appearing as if the room is very big. Same way on the right side also, here if you consider, there is a plane mirror over here onto the left side, onto the right side over here. That is the reason I am able to see the image of the wall clock onto the right side also over here. So this makes the rooms appear to be bigger. That is what we mean by false dimensions. Apart from that, we are also having one of the important use, that is in the solar cookers. In the solar cooker, what we do is that we'll fix a plane mirror to the lid of the solar cooker, preferably the box type of the solar cooker, where the sunlight incident on the mirror over here on the lid, okay, that is getting reflected, and there is a large amount of sunlight receiving into the box type of solar cooker, which will help the items being cooked faster. Okay, this is one of the use of it. The other use of the plane mirrors is in periscopes or kaleidoscopes. In the case of periscopes, we do have a structure like this Z-like structure, where this is the top tube-like structure, this is the bottom tube-like structure, and we do have 2 plane mirrors here, each of them inclined 45 degrees with the horizontal. Okay, so in the case of this periscopes, what is happening is this: the lateral inversion which is occurring in the top mirror over here is getting again lateral inverted, so that lateral inversion caused by the first mirror over here is nullified by the lateral inversion occurred by the second mirror. So we will be able to see a person who is at the top portion over here, at the bottom portion over here. Generally, these kind of periscopes are used in the submarines as well as in the warfare also. Clear? So far we have discussed about the reflection, types of reflection, images formed by the plane mirrors and their characteristics and the uses of it. Hope these things are clear for you. Having discussed about the plane mirrors, let us now look ahead at another type of mirrors called spherical mirrors. Okay. If you wanted to understand what is a spherical mirror, we need to consider a hollow sphere, and that from that hollow sphere we are making out a spherical mirror. Here I am considering a hollow sphere and I am cutting this particular hollow sphere at this point. If I take out the cut portion, separate it out like that, then whatever the part we are getting, I can make this glass piece into a spherical mirror. How do I make this glass piece into a spherical mirror? By silver coating it. Okay. Inner surface of the spherical piece, when you consider it one, is called concave surface. The outer part of the spherical piece, whatever you are making it out of the hollow sphere, you call it as the convex surface. Now, this particular concave or convex, either of these two surfaces, if I coat one side with silver coating, then the other side will be the reflecting surface. Suppose I silver coat on the outer surface, which is called as the bulged out or the convex surface, then automatically the inner surface will be the reflecting surface. Such a mirror you will call it as a concave mirror. Okay. If you take an object and place it in front of the concave mirror, I'll be able to get an image like this. So there is still time. We'll discuss about the nature of the images formed by concave mirrors also. Now let us look at a convex mirror. Like in the case of a concave mirror, the bulged out portion was silver coated. Now if you silver coat the bulged in portion or the concave portion, if you silver coat it, the bulged out portion or the convex portion will be the reflecting surface. Such a mirror you will call it as a convex mirror. One of the example is something like this, which is placed at the crossroads of a road. Okay. Before knowing further about the images formed by these spherical mirrors, we need to know some of the important terms related to the spherical mirrors. So for this, I am considering a convex mirror. Okay. Now, what are the convex mirror? If I am taking the geometric center of that particular convex mirror, if you see, that is called as a pole. So generally denoted by the letter P. Okay. The next important term is the center of curvature. When I consider the center of curvature, it is nothing but the center of the spherical surface. Okay. The center of the sphere from which this particular convex mirror was made of. Okay. That is called the center of curvature. Now from the center C to any point on the mirror, if I draw a line joining the center and any point on the line, any point on the mirror, that will be nothing but radius of curvature. Okay. So here I am showing the radius of curvature, say from C to P. P is a point on the mirror, the pole, the geometric center. So from the pole to the center, this particular distance I can consider to be the radius of curvature. Radius of curvature is not restricted only from C to P, but from C to any point on the mirror. Clear? Now, if I draw a line passing through C and to P, joining these 2 points C and P, if I draw a line extended to on either sides, then this particular line is called as a principal axis. Please note the spelling principal, principal axis. Okay, this is a very important axis what we consider. This is a very important term. Okay, so because the nature of the images and everything are related to, are taken with this as the reference. Clear? Now there is one more point called focus, that is principal focus. The principal focus for a spherical mirror will be lying between the C and P, the center of curvature and the pole of the mirror. Between these two, I will have the focus. Okay. So one more distance we will consider, that is the distance between the focus, principal focus and the pole. That is called the focal length. Okay. So you can see very clearly, I have here two distances. One is the radius of curvature, another is the focal length. Rest all the things are the positions. Pole, focus, center of curvature, all these are the positions. Only the radius of curvature and the focal length are the distances. Clear? Hope all the terms related to the spherical mirrors are clear to you. Understanding the terms over here, I said there are two distances between the two. There are two distances here what we discussed, that is radius of curvature and focal length. We'll try to now find out the relation between the two, that is the focal length and the radius of curvature. I am considering a concave mirror for that. Here in this particular image, I am having this is the principal focus. So the F is the principal focus and this line is the principal axis. There is a light ray coming parallel to the principal axis incident on the mirror at the point M. The inner surface is the reflecting surface. That is the reason it is called a concave mirror. And this reflected ray is passing through the focus over here. Okay. From the center C, if I am drawing a line over here to the point M, okay, C to M is the radius of curvature. It is also equal to C to P. As I mentioned earlier, from the center to any point on the mirror, if you draw a line, that line length will be equal to the radius of curvature. Now, this particular line C to M will be normal to the mirror at the point M, because C is the center of curvature, that means the center of the sphere. So CM being the radius, this radius of a circle will be perpendicular to the point on the circumference. If I draw a tangent, that tangent will be perpendicular to the radius. We all know very well about it. Okay, so that is the reason here this particular CM will be normal at the point M. In such case, what will happen? The angle between the incident ray and this CM will be the angle of incidence I, and the angle between the reflected ray and the CM will be the angle of reflection R. So angle I is equal to angle R. We all know that because it follows the laws of reflection. Okay. Now, if you consider this particular figure, you can see very clearly. Let me show you. This particular angle here, say theta. This theta is equal to I. How? If I consider this light ray, which is parallel to the principal axis, okay, CM can act as a transversal. So I will be equal to theta because these two are alternate angles. Okay. And we know from the laws of reflection that angle I is equal to angle R. So I can write the expressions like this. I is equal to R. Let me take it as first equation. Now I also got that I is equal to theta. I explained you why I is equal to theta. Let me write clearly. Okay, this is second. So from these two equations, I can conclude that theta is equal to R. Yes or no? So if implies that theta is equal to r. So now if I consider the triangle CFM, in that particular triangle I have theta is equal to r, which implies that the side CF of the triangle CFM is equal to the side FM of this particular triangle. Why? When theta is equal to r, the triangle CFM will become an isosceles triangle. In an isosceles triangle, the sides opposite to equal angles in an isosceles triangle will be equal. Okay, that is the reason this will become an isosceles triangle, because the two angles are equal. Okay, if you recall the basics in geometry, we will be able to get when theta is equal to r, this is CF is equal to FM. Fine. Now, thing is that when the aperture of the mirror is very small, okay, now we'll consider this mirror as mirror of very small aperture. When I say mirror of aperture is very small, what do I mean by aperture? This point to be noted. The total mirror which is exposed to the light, that is what you call aperture. You will measure aperture by its diameter. What is the diameter of the mirror over here? From this particular end to this particular end, if I draw a line like this, okay, this total diameter of this particular spherical mirror part will be called as the aperture. This is a measure of the aperture. Okay, now if I consider the mirror of a small aperture, then what is happening is this: I will have an assumption that FM is equal to FP. Okay, when FM is equal to FP, I can also write CF is equal to FP. When CF is equal to FP, and if I consider the total from C to P, the distance, it will be equal to double the distance of F to P. And F to P is nothing but focal length F. And C to P is nothing but the radius of curvature R. That means R is equal to 2 times the focal length R. Focal length is equal to half of the radius of curvature. I have derived this expression using a concave mirror. Okay, same thing you can also do by taking a convex mirror. Try this as a homework. Okay. Now, before you try this as a homework, we need to understand how the light rays, which are incident on spherical mirrors, will have a pattern in reflection. Okay. So, for that purpose, we need to know some points like rules for construction of the ray diagrams. Okay. So, what are the different rules what we have to construct ray diagram? Basically, when you say ray diagram, what do you mean by ray diagram? A diagram on which a mirror, a plane mirror or a spherical mirror we have, and there is an object. From the object, the light rays are coming an incident on the mirror. After reflection, how they are getting reflected? Are they diverging or converging? If they are converging, at what point they are converging? And if they are diverging, from what point they appear to diverge? If you are able to trace all these things, then you will be able to study about the nature of the images formed by these mirrors. Okay, so we need to understand how the light rays incident on the spherical mirrors will behave when they come through or when they pass through different positions. Clear? Let us see the rules for the construction of the ray diagrams. I am considering the pole of the concave mirror here. Okay, then the center of curvature, point C. From C, there is a line joining to the P and extending on either sides. Recall, this is nothing but principal axis of the concave mirror. Okay, now I'll consider a parallel beam of light parallel to the principal axis coming an incident on the concave mirror. So after reflection, these light rays will pass through this particular point on the principal axis. This is nothing but the focus, the principal focus. So the rule is that in the case of a concave mirror, okay, if I have a parallel beam of light parallel to the principal axis, then after reflection, they will pass through the focus. Now let us consider if such a parallel beam of light is incident on a convex mirror, then what will happen? So I'm considering a convex mirror. Now I'll consider the pole of the mirror, the center of curvature, the principal axis. Okay. Now I will have a parallel beam of light incident on the convex mirror parallel to the principal axis. Okay. Now what are the reflections that are happening? All the reflected rays, they are going this way. If you see very clearly, as the reflected rays progress, they move away from each other. That means they form a divergent beam. Okay, so they cannot form an image on the right side of the mirror. So what we need to do, we will try to reproduce them back so that they will be appearing to come from a single point, and that is the principal focus. Okay, so in the case of a concave mirror, a parallel beam of light parallel to the principal axis after reflection will pass through the focus, whereas in the case of a convex mirror, a parallel beam of light parallel to the principal axis after reflection, okay, will appear to diverge from the focus. This is the first rule. Hope this is clear. Okay. Now we'll consider another type of light ray. Okay. Here I am considering again a concave mirror. Earlier I considered the light rays passing parallel to the principal axis. Now I will consider the light rays passing through the focus. Now you guess in what direction they should go? Yes, they should go. After reflection, they will pass parallel to the principal axis. So the point is clear. The light rays can retrace their path. If the light ray is incident coming parallel to the principal axis on the mirror, after reflection will pass through the principal focus. If the light ray is incident through the focus, after reflection will go parallel to the principal axis. Okay, this is the case of a concave mirror. Let us see a similar case in the case of a convex mirror also. This is the case of a concave mirror. Okay, let us see a similar case for a convex mirror also. What is happening? Here I am considering the convex mirror, principal axis, center of curvature, pole. Now the light rays should be directing towards the principal focus. So I am considering an incident beam, which is a convergent beam. They appear to converge at the focus. That means these light rays are directed towards the focus of a convex mirror. But they are not reaching over here. Fine. They are getting reflected at this particular mirror surface. So in what way do they behave after reflection? Very clear. They will go parallel to the principal axis. The light rays cannot meet at this point, right? So they appear to converge at this point. So after reflection, they go parallel to the principal axis. Clear? Let us now consider one more light ray. This time I am taking one more time a concave mirror and I am considering a ray through the center of curvature. Any number of light rays through the center of curvature, they are incident on the concave mirrors. Such a case, what is happening? They are again getting retraced. Okay, they pass through the focus, they pass through the center of curvature again. Why? Because from the center of curvature to any point on the mirror, if I draw a line, that line will be normal to that particular point on the mirror. So in such a case, what is happening? Angle of incidence is equal to 0. Therefore, the angle of reflection is also equal to 0. Clear? So now what is happening? When I have a beam of light rays, a divergent beam of light rays from the center of curvature, they are incident on the concave mirror. They retrace their path. Let us now look at the similar case for a convex mirror. Now I should have the light rays directed towards the center of curvature, not to the focus. So let us draw them, produce them ahead so that they will meet at the center of curvature. Okay, fine. Now what will happen? Again the same phenomena. They will get reflected from that point and they are again divergent. So whatever the light ray is incident on the convex mirror, which is directed towards the center of curvature, will retrace its path. Very clear, right? Able to understand? So these are some of the rules for construction of ray diagrams. Clear? Let us summarize those points over here. So if any ray of light traveling parallel to the principal axis after reflection either passes or appear to diverge from the principal focus. Okay, they'll pass through the principal focus in the case of a concave mirror. They appear to diverge from the principal focus in the case of a convex mirror. Okay, next, if a ray of light initially passes through, that means a concave mirror, or appears to pass through a convex mirror, the principal focus of the spherical mirror after reflection travels parallel to the principal axis. Okay. So first point is parallel to the principal axis. Second is passing through or directed towards the focus. Okay. Let us consider the third point. If any ray of light incidents obliquely at the pole of a spherical mirror, it reflects from the pole such that the angle of incidence is always equal to the angle of reflection. Okay, this is also one of the important points to be remembered. Okay, finally we have, if a spherical mirror, in any spherical mirror, any line that joins the center of curvature with a point on the mirror is normal to the surface of that point. So any light ray incident normally on the mirror gets reflected normally and retraces its path. In such case, what is happening? The angle of incidence is equal to 0, so the angle of reflection is also equal to 0. That is the reason the light rays are retracing their path. Okay. Hope whatever the points so far we discussed are clear to you. Okay. In this session, we have discussed so far about what is reflection of light, what is light basically, then what is reflection of light. Okay. What is a point object, what is an extended object, and what are the laws of reflection. In the case of laws of reflection, we have discussed that the angle of incidence is equal to the angle of reflection, and the reflected ray, the incident ray, the normal at the point of incidence all lie in the same plane. We also have discussed about the uses of plane mirrors. We also discussed about spherical mirrors. The spherical mirrors are the mirrors formed out of glass spheres. If the inner portion of the sphere is reflecting surface, then we call it as a concave mirror. If the outer portion of the spherical surface is reflecting surface, then we'll call it as a convex mirror. Okay, and the terms related to the spherical mirrors also we discussed. Terms like pole, center of curvature, radius of curvature, principal axis, principal focus, focal length. Clear. We also have seen about how the incident light ray on a spherical mirror will get reflected both in the case of concave and convex mirrors. Okay. We'll discuss some more points in the next session. Okay. Have a good day until then. Thank you.